This experiment broke one of the basic rules of physics, and no one expected it to work. And when they ran it anyway, the results didn't just surprise physicists. They forced us to rewrite something we thought we understood completely. I'm Richard Feynman, and I want to tell you about an experiment that frankly should not be possible. Not because we lacked the technology, not because the math was too hard, but because everything we believed about the nature of reality said it couldn't happen, and yet it did. Now, before I get into the experiment itself, I need to take you back to something fundamental, something that sits at the very heart of quantum mechanics and honestly at the heart of my own career. It's called the double-slit experiment. You may have heard of it, but I promise you, you haven't truly felt the weight of what it means. Here's the setup. You take a barrier, you cut two thin slits into it. Then you fire particles, let's say electrons, one at a time toward that barrier. On the other side, you have a detector screen. Simple enough, right? You'd expect the electrons to pass through one slit or the other and pile up in two bands on the screen. That's what any reasonable person would expect, but that's not what happens. What you actually get is an interference pattern, alternating bands of light and dark like waves overlapping in water. The electron, a single particle fired alone, somehow passes through both slits at the same time. It interferes with itself and lands in a pattern that can only be explained if it traveled as a wave, spread across both slits simultaneously. Now here's where it gets really strange. If you get curious, as any good scientist should, and you set up a detector to watch which slit the electron goes through, the interference pattern disappears. The moment you observe it, the electron behaves like a particle again. It picks one slit. It lands in one of two bands, normal, boring, classical. The act of observation changes the outcome. I used to say that the double-slit experiment contains the only mystery of quantum mechanics. Everything else, all the strange predictions, all the weirdness, is just variations on this one thing. The particle doesn't have a definite position until you look. Until then, it exists in a superposition, a blur of possibilities. Now, most physicists accepted this. We moved on. We built quantum electrodynamics, transistors, lasers, MRI machines. The theory worked. We didn't ask too many uncomfortable questions, but some people kept asking. And one of the most persistent questions was this, like where exactly does the quantum world end and the classical world begin? Electrons behave this way, atoms behave this way, but what about something bigger? What about a molecule? What about something you can almost see with your naked eye? This is where the experiment I want to tell you about comes in. In 1999, a team of physicists in Vienna, led by Anton Zeilinger, did something remarkable. They took a molecule, not an electron, not an atom, but a proper molecule called carbon-60. You may know it as a buckyball, 60 carbon atoms arranged in a beautiful soccer ball shape. It was, at the time, the largest object ever used in a quantum interference experiment, and they fired it through a double slit. Now let me make sure you appreciate the audacity of this. A buckyball is not small by quantum standards. It has hundreds of particles inside it. It's warm, it vibrates, it radiates energy, it interacts with its environment constantly. Every single thing we know about how quantum coherence breaks down said that a molecule this large should behave classically. It should pick a slit, it should land in a band, no interference, but they got the interference pattern. A molecule made of 60 atoms went through both slits at once. It interfered with itself. It behaved against all reasonable expectation like a quantum wave. I'll be honest with you, when I think about this result even now, it gives me a particular feeling. It's not quite surprise because quantum mechanics predicted it should be possible in principle, but it's something like awe. Because here's the thing, when we keep assuming there's a line, a boundary, below this line, quantum, above it, classical, and nature keeps refusing to give us that line. But the Vienna experiment, as stunning as it was, is not the experiment I'm really here to talk about, because the story didn't stop there. Over the following years, the same group and others kept pushing. They used bigger and bigger molecules. They refined their techniques. They got better at isolating particles from the environment, from air molecules, from stray electromagnetic fields, because all of those things can destroy quantum coherence. All of those things can act like an observer and collapse the wave. And in 2019, 20 years after the buckyball experiment, they did something that genuinely stopped the physics community cold. They demonstrated quantum interference with molecules containing nearly 2,000 atoms. Let me repeat that. nearly 2,000 atoms, moving through a double-slit setup, interfering with themselves, producing a quantum wave pattern. These molecules were so large that if you laid them end to end with other molecules of their kind, you'd see them under certain electron microscopes. They had molecular weights thousands of times greater than anything previously shown to exhibit quantum behavior. They were, by any previous measure, macroscopic, and they still went through both slits at once. Now, I need to explain to you why this is so much more than just a bigger version of the buckyball experiment. Because when you scale up like this, you run into a problem that becomes absolutely brutal at larger scales. It's called decoherence. Decoherence is what happens when a quantum system interacts with its environment. And by environment, I mean anything outside the system: air molecules, photons, vibrations, heat. Every single one of those interactions is, in a sense, a measurement. Every time your quantum particle bumps into something in the outside world, that outside world gains information about where the particle is. And as soon as the environment has information about which path the particle took, the interference disappears. It's not mystical. It's actually very precise and very calculable. The more massive your object, the more it interacts with its environment. The more it interacts, the faster decoherence happens. And decoherence happens fast. We're talking timescales that are almost incomprehensibly short for anything larger than a few atoms. To run this experiment with 2,000 atom molecules, the team had to do something extraordinary. They had to build what is essentially the most perfectly isolated quantum environment ever created for this purpose. Ultra-high vacuum, air pressure so low it makes outer space look crowded, extremely careful thermal management so the molecules wouldn't radiate too much heat, a detection system sensitive enough to catch individual molecules landing on a surface, one by one, over hours and hours, until the pattern slowly emerged, and it still almost didn't work. The window of coherence for these molecules, even in perfect vacuum, is extraordinarily thin. The experiment ran right at the edge of what was theoretically possible. That's what I mean when I say this experiment shouldn't be possible. Not that the physics forbids it. The physics actually predicts it, barely, at the very limit of our ability to isolate a system, but that everything about the physical world conspires against you. Gravity, heat, air, light, they all want to collapse your quantum state. They all want to force the molecule to make a decision about which path it took. And yet, let me now tell you what this means, because I don't want you to walk away thinking this is just a record-breaking stunt. Look how big a molecule we used. Congratulations, have a trophy. This experiment is telling us something profound about the structure of reality. The first thing it tells us is that quantum mechanics does not have a natural upper limit. There is no scale at which the laws change. There is no magical threshold where particles stop being quantum and start being classical. The only reason your chair doesn't tunnel through the floor, the only reason you don't diffract when you walk through a doorway, is that decoherence happens so catastrophically fast at human scales that quantum effects are completely washed out before they can manifest. But they're still there, in principle. The quantum rules still apply. They're just buried under an avalanche of environmental interaction. The second thing it tells us is that quantum coherence, this delicate, strange condition of being in multiple states at once, is far more robust than we thought. Given the right environment, given sufficient isolation, matter at scales we never expected can maintain this property, can exist as a wave, can take multiple paths simultaneously. And the third thing, and this one I find the most philosophically striking, is that it deepens the measurement problem rather than solving it. Let me explain what I mean by that. When we talk about quantum mechanics and observation collapsing a wave function, the uncomfortable question has always been, what counts as an observation? Is it a conscious observer? Is it a measuring device? Is it any physical interaction whatsoever? Most physicists today, myself included, would say it's any physical interaction that transfers information to the environment. That's decoherence. That's the mechanism. There's no need for a conscious observer. The universe doesn't care if you're watching. What matters is whether the environment has been disturbed in a way that records which path the particle took. But here's what these experiments force you to confront. These enormous molecules in perfect vacuum maintain quantum coherence. They take both paths. No interference from the outside world. Fine. But the moment they hit the detector screen, the moment they interact with the material of the screen, they land at a single point. The wave function collapses. The molecule picks a location. Why? Why does interacting with the detector screen count as a measurement, but traveling through vacuum does not? What is fundamentally different about those two interactions? The honest answer is, we think we know, but we are not completely certain. The detector is not perfectly isolated. It's at room temperature. It's coupled to a thermal bath of billions of atoms. The information about where the molecule landed propagates outward into the environment essentially instantaneously and irreversibly. That irreversibility, that one-wayness, seems to be the key. But this is still, at some level, a matter of degree. It's a quantitative difference, not a qualitative one. And that should make us uncomfortable. It means the line between quantum and classical is not a line at all, it's a gradient. And somewhere along that gradient, things we think of as definite and real emerge from things that are indefinite and wave-like. And we still do not fully understand exactly how. I want to talk about one more layer to this story, because I think it's the most important one. These experiments are not just interesting physics. They are the foundation of something that is being built right now in laboratories around the world. The future I'm about to describe is not speculation. It is the direct engineering consequence of what these experiments confirm. If large molecules can maintain quantum coherence, then, under the right conditions, so can larger and more complex systems. And if a system can be held in a coherent quantum state, it can do something classical systems cannot do. It can process information in a fundamentally different way. This is quantum computing. And I don't mean the vague pop science version where a quantum computer is just a very fast classical computer. I mean something genuinely different. A classical bit is either 0 or 1. A quantum bit, a qubit, can be 0 and 1, and every combination of both simultaneously. It processes all possible answers at once, interfering like a wave, and when you measure the result, the correct answer is the one that constructive interference has amplified. The experiments I've described are proof of principle for this. They demonstrate that quantum coherence is real, that it survives in large systems under the right conditions, and that the engineering challenge, while brutal, is not impossible. We are in the early days of building machines that think quantumly, and the double-slit experiment in all its variations and extensions is the conceptual bedrock beneath them. But I want to be honest with you because I think honesty is more valuable than comfort. We do not fully understand quantum mechanics. I know that's a strange thing to say about a theory that predicts experimental results to 10 decimal places, that underpins essentially all of modern electronics, that has never once been wrong in a testable prediction. But there is a difference between being able to calculate with a theory and understanding what it means. When I calculate with quantum mechanics, when I use the rules, apply the mathematics, crank through the formalism, I get right answers, always, spectacularly right answers. The theory is, in a computational sense, perfect. But when I ask what is actually happening, what is real, I run into a wall. Is the electron really in both places at once before I measure it? Is the wave function a real physical thing or just a calculating tool? When the wave function collapses, does it collapse everywhere in the universe instantaneously? If so, what happened to relativity? These are not fringe questions. They are the questions that Einstein, Bohr, Heisenberg, Schrödinger, Bell, and every serious physicist since has wrestled with, and they remain unanswered. I once said that I think I can safely say that nobody understands quantum mechanics. I meant it, and I still mean it. Not as a confession of defeat, but as an invitation, as a reminder that the most successful physical theory in human history still hides something from us, still points at a door we haven't opened. The experiment I described today, the 2000 atom interference, is a key in our hand. It confirms that the quantum world is larger than we thought. It pushes the mystery further into the macroscopic realm. It tells us that whatever quantum reality is, it doesn't end at the atomic scale. And it raises a question I find genuinely thrilling and genuinely unsettling. If molecules of 2000 atoms can be quantum, if in principle the laws apply at all scales, if the only thing separating the quantum world from the classical world is decoherence, a practical barrier, not a fundamental one, then where does it end? Is a bacterium quantum? Under the right conditions, some researchers believe photosynthesis and bird navigation exploit quantum coherence in living systems. Is the brain quantum? There are serious physicists who believe consciousness itself may be tied to quantum processes in neural tissue. I'm not endorsing these ideas. The evidence is contested, but they are not crazy. They are the natural extension of asking, if the line doesn't exist at 2,000 atoms, when does it appear? And if it never appears, if quantum mechanics applies in principle all the way up, then the universe you live in is not the solid, definite, one path at a time universe it appears to be. It is a universe of superpositions, of interference, of probability waves that collapse into apparent reality only when they can no longer avoid it. You are, in a sense, the experiment. Every object you see, every particle in your body, every photon striking your retina, all of it obeys these rules. All of it was, at some point, a quantum system. The classical world you inhabit is not the opposite of the quantum world. It is the quantum world, seen from the inside after decoherence has done its work. I find that remarkable. I think you should too. The experiment shouldn't have been possible, but it was. And that's the most exciting sentence in science. Because every time an experiment that shouldn't work does work, it means our picture of reality just got a little more honest, a little less comfortable, and a little more true. I'm Richard Feynman, and if you're not confused by now, you haven't been paying attention.